Hello viewers, this is your science bro. Today I've brought for you a video on determining the molecular formula of an organic compound through combustion. So we are going to look at combustion of a hydrocarbon, then we use that data to determine the molecular formula. But particularly, students have been requesting this video about contraction in volume. That's why particularly I'm discussing only contraction in volume. Of course, it has other direct questions, but I'm here on contraction in volume. Now, before I start, I request those who have never subscribed, hit the subscribe button just below this video. Let's go on now. Now, before we look at the questions direct, let us look at the approach to the questions first. Let us go through the theory, how we handle these contraction volume questions and the related formulas. Now, when we burn a hydrocarbon, let's say this hydrocarbon general formula. Every student, I hope, has this formula at the fingertips. Has this formula at the fingertips, producing carbon dioxide and water. Water condenses to a liquid, and we have that. Now, we realize that this experiment for combustion of hydrocarbons has two stages. The first stage, we burn the hydrocarbon, then we cool the gaseous mixture to condense of water vapor, then we pass the mixture through concentrated sodium hydroxide or potassium hydroxide. So the first stage here, now we should first acknowledge that this oxygen that we use should be excess. That means part of it will react, so we have reacted oxygen, then part of it will go unreacted oxygen here. So oxygen is excess containing these two. Now let's look at the first stage. First stage, the gaseous products, the first stage after combustion, then before you cool. When we burn, we produce carbon dioxide and water vapor, but part of the oxygen goes unreacted. So I will have carbon dioxide, water vapor, unreacted oxygen. Then I cool the mixture. So to leave me with the gases only having unreacted oxygen and volume of carbon dioxide. So first stage, I have volume of carbon dioxide plus volume of unreacted oxygen. So I have two there. Now, at the first stage, this is what I have. Then the second stage, we pass this mixture through potassium hydroxide or sodium hydroxide, then it absorbs of carbon dioxide. So second stage here. So what do I have? When I pass through potassium hydroxide, I remain with unreacted oxygen. So second stage, I have volume of unreacted oxygen. But in each of these stages, there is a contraction because here water condenses off, so there is a volume reduction. So we have first contraction. Now the contraction can be mentioned as a reduction or a fall in volume or a diminution, any of those words. So in the first contraction here, contraction we consider it as the initial volume minus final volume. But we are looking at the first very stage here. Initial volume, what are introducing in the container? You are introducing a hydrocarbon. So I have volume of hydrocarbon. Then I added in excess gas, so I have these two, reacted oxygen and unreacted oxygen. So these are the three volumes at the first stage when you are starting the experiment. Then at that first stage, I have carbon dioxide and water vapor, carbon dioxide and unreacted oxygen. So volume, carbon dioxide plus volume of unreacted oxygen. So mathematically, both of these are volumes, but because of space, so I'll subtract this, we'll go with this. So the first contraction here, contraction in volume, contraction in volume here will equal to volume of hydrocarbon plus volume of reacted oxygen. Hydrocarbon plus volume of reacted oxygen. Then we are subtracting volume of carbon dioxide. So that's the first stage of contraction. This is the formula. So the second stage, you said it is actually what remains here, the second contraction. What is? So since the second contraction occurs after passing the gaseous mixture through potassium hydroxide, that means the reduction is because of absorption of carbon dioxide. That means this would be exactly the volume of carbon dioxide. I think we notice that. So this is the simple theory. But now we are going to get the volume of reacted gas, volume of carbon dioxide by the reacted mole ratio. We can, if this is 1 to x plus y out of 4, this is 1 to x for carbon dioxide. So in case I have here 10, this would be 10, reacted oxygen will be 10 into this, carbon dioxide will be 10x. So that's a simple theory that we are going to be using in this calculation. Let's dive into question 1. Let's look at example 1. On sparking 10 cubic centimeters of a hydrocarbon, they introduce 10 cubic centimeters, so volume, producing 10 here. Hydrocarbon with excess oxygen, there was a contraction in the volume. This is the first contraction after cooling. So when the gaseous mixture was passed through concentrated sodium hydroxide, further contraction of 40 occurred. This is the volume of carbon dioxide. This is actually, question would have even said there was a reduction or there was a fall in volume of 40. That was the absorbed carbon dioxide. So it's actually 40 cubic centimeters. Now we can have this as carbon dioxide in terms of 10, mole ratio is 1 to x will be 10x. Because you would either say 10x for this, so this is also 10x, so it will be equal to this, and you get x as actually 4. Or else you can have it alternatively by just mere dividing, just divide through the ratio. You can get 10 out of 10. This is 40 out of 10, and this is the x value. So x can be got in those two ways there. So let's go and interpret this first contraction here. So first contraction in volume would equal to, we said, its volume after the formula of the hydrocarbon plus volume of reacted oxygen, then minus volume of carbon dioxide. So the hydrocarbon volume here it's 10, we introduce in 10. Now the reacted oxygen here it's 10 into x plus y out of 4 by mole ratio. This is 1 to this. So if this is 10, this is 10 into this. So this is the first contraction was 25. 25 equals 10 plus this. Then carbon dioxide, we can either say 10x here, or we can use 40 and make sure that we replace the value of x as 4 here. So you can directly say 10x, since I'm going to subtract the algebra. So you can use 25 is equal to 10 plus 10x plus, this is now 2.5y minus 10x. So this and this can go, giving us 15 is equal to 2.5y. So y can give us about, and punch the calculator, 15 divided by 2.5, that's roughly 6. So we can say molecular formula. Molecular formula is C4H6. So that's the molecular formula. Let us look at question 2. On sparking 5.2 cubic centimeters of a hydrocarbon with excess oxygen, there was a contraction in the volume of 7.8. This is a first contraction. Then when the gaseous mixture was passed through concentrated sodium hydroxide, there was a further contraction of 10.4. This is a second contraction because this is the volume of carbon dioxide. Determine the molecular formula of the hydrocarbon. Let's feed in that information. 5.2 cubic centimeters. Then the reacted here would be 5.2 into x plus y out of 4. Then this one is 5.2x by molar ratio of 1 to x here, 5.2x. So the first contraction is 7.8, the second contraction is 10.4, which is the volume of carbon dioxide. So this 5.2 is equal to 10.4. So 5.2 is equal to 10.4. So you can solve for that. Let's get the calculator. 10.4 divided by 5.2, giving us 2. So this x is 2. Now let's interpret this contraction here, which is 7.8. First contraction in volume is actually volume of this plus volume of reacted gas, reacted oxygen, minus volume of carbon dioxide. So I'm going to punch in those values. So this is 7.8 is equal to hydrocarbon is 5.2 plus reacted oxygen is 5.2 into x plus y out of 4 minus carbon dioxide 5.2 x here. We said we can use 10.4 provided you'll put here 2. This x is 2. So that's pretty simple. Punching into the calculator, this is 5.2x, will cancel with this. So I'll have 7.8 minus 5.2. 7.8 minus 5.2 gives us 2.6 equals, so this one is going to be 5.2 y out of 4. So giving you finally, so times 4 divided by 5.2, giving us 2. So you say molecular formula is C2H2. Let's look at question 3. 10 cubic centimeters of a gaseous hydrocarbon Q was exploded with excess oxygen. On cooling, the reduction in volume was this. If the vapor density is 3.48 exponent negative 3 at STP, find the molecular formula of Q. They have only given us the first contraction here. So let's interpret this contraction first. So the hydrocarbon is 10 cubic centimeters. So if this is 10, let me remove these units. So if this is 10, this one is 10 into x plus y out of 4, then this is 10x by this. So this contraction of 25 would be 25 is equal to, said volume of hydrocarbon 10 plus volume of reacted oxygen, then minus volume of carbon dioxide. So by handling the mass, 25 minus 10 is 15, giving us 10x, cancelling with that. So it gives us 2.5y. So let's divide there. So 15 divided by 2.5 gives us 6. So y is 6. But since they gave us the vapor density with units, here we have to convert it to the molecular mass by interpreting 3.48 to power 3.48 exponent negative 3 grams in 1 cubic centimeters. So at STP, so 1 cubic centimeter from this interpretation, 1 cubic centimeter contains 3.48 times 10 per negative 3 grams of Q. So out of the 400 cubic centimeters at STP contain 3.48 negative 3, then we multiply by this 400 grams of Q. So that will give us, let's dive into that, 3.48 exponent negative 3, then times 400, gives us 77.952. So let's now go back to this formula. CXHY is equal to 77.952. Since Y is known, so it is 12 times X plus 1 times our Y, which is 6, gives us 77.952. So you solve the math. So 77.952 minus 6. Then we are dividing it by 12. Gives us 6 and rounding off. So X equal to 6. So actually the molecular formula is C6H5. That's what you do. Let's look at question 4. When a gaseous alkene is burnt completely in excess oxygen and cooled, there was a contraction in volume equal to double the volume of the hydrocarbon was noticed. Determine the molecular formula of the alkene. Since the question is specific, let's use the alkene formula. So alkenes is generally this, but you can use the other one, CXHY, but since it has little information, it will be difficult to handle the unknowns. So this has one unknown, so it's a gaseous alkene. So let's try to write this, giving us carbon dioxide plus water. So let's balance. Carbon is N, put N here. Hydrogen is 2N, I just need N here. So making oxygen 2N plus N, that is 3N. So I'll need 3N out of 2. Now, the contraction that occurs was double the volume of the hydrocarbon. So we have to let this volume be V cubic centimeters. So this by mole ratio will be 3N out of 2V, then this will be NV. So let's look at the contraction. The contraction was double the volume. So contraction is 2V, which is double this volume. We say this volume plus reacted gas minus carbon dioxide. So it is this plus this, subtract this is equal to that contraction there. So let's simplify the algebra. So this 2V minus V is going to give us a V. So this is V, 2V minus V is V. So this is going to be, apply some math there. So this is 3NV minus 2NV out of 2. So this gives us 2V, giving us NV. And actually N is equal to 2. So that's the algebra simplified. So you can go back here and say molecular formula is C2H4. If you substitute for N there. Let us look at question 5. When 20 cubic of a gaseous hydrocarbon, so that one I'll go back this formula, plus this, giving us this, plus this, liquid. So introduced volume is 20. So reacted is 20 into X plus Y out of 4. the produce is 20x here. The volume contraction, of course, there is cooling, but though the question has not shown it there, the volume contraction was 60. That's the first contraction. And when passed through concentrated potassium hydroxide, there was a further contraction of 60. So this is the volume of carbon dioxide. So you can equally say 20x is equal to 60. So this 20x will equal to 60. So 20x equal to 60, meaning x is equal to 3. Let's try to go further. The first contraction was 60. So you can use that 60. 60 is equal to initial volume is 20 plus this plus 20 into x plus y out of 4. Then minus the volume of carbon dioxide, which is 20x. So you realize that this 20x and this 20x will die. So this is 60 minus 20 is equal to 40. This is 40 is equal to, so this 20x has died with this. So I have 20y out of 4, which is 5y. So giving us y is equal to 8. So you can say molecular formula is C3H8. Now a student will say, why didn't you use this 120? Let's see another method if we can involve 120 there. So I can try to remove this. Method 2. Look at method 2. Now in method 2, we want to involve this 120, that is the volume of excess oxygen. Now let's first look at the introduced volume. So total initial volume. So what have we introduced? We introduced the 20 plus the 120. So 20 plus 120 giving us 140 cubic centimeters. So that's what we introduced in. But in the first stage, there was a contraction of 60 or a reduction of 60. So remaining volume would be 140 minus this reduction, which is the 60, giving us about 80 cubic centimeters. Now, in terms of these unknowns, what is the remaining volume? We said first stage contains volume of carbon dioxide and volume of unreacted oxygen, because part of oxygen reacted. So the 80 would equal to actually volume of carbon dioxide, which is the 20 plus unreacted oxygen. Remember, this is the reacted oxygen, but we introduced 120. So unreacted oxygen would be 120 minus this reacted here. So this reacted is this y out of 4. So let's simplify the math. So it's 80 is equal to, so you can have 80 minus 120 giving us negative 40. So this is 20x minus this one will give us 0. So this will die with this negative 20. Giving us negative 20 out of 4, which is negative 5y, and y is about 8. But of course, we know that 20x is actually equal to this reduction, to this second contraction. So we can have this 20x equaling to 60, and x becomes 3. So molecular formula is C3H8. Thank you.